Hello, this is Sruthi Penmetsa, and today I'm going to talk about carbon nanotubes.
These are the topics that will be covered in the presentation.
What are carbon nanotubes? Carbon nanotubes or CNTs are allotropes of carbon in the tubular form with diameter as small as 1 nanometer and lengths of few nanometers or microns. They are viewed as rolled up graphene sheets. The CNTs are characterized by its chiral vector and tube axis or translation axis. The chiral vector is a combination of n, m, and theta, which is the chiral angle with respect to the zigzag axis. These cylindrical carbon molecules have interesting properties resulting from the cylindrical shape, strong carbon-carbon covalent bonds, and lack of surface tangling bonds that make them potentially useful in many applications such as in nanotechnology, electronics, optics, and other fields of material science, as well as in architectural fields. They exhibit extraordinary strength and unique electrical properties and are efficient conductors of heat. Their final usage, however, is limited due to their potential toxicity. So why CNT? As years pass, the transistors have been getting smaller and smaller to pack more transistors on a single chip. Due to this, a lot of power is being wasted and heat is being generated. The MOSFETs are reaching a limit and their size cannot be reduced any further. With the change in the channel material and using CNT instead of silicon, these limits can be overcome. According to the researchers, the carbon nanotubes can offer up to 3 times reduction in power and increase the performance by 3 times too. What are the different types of CNTs? CNTs are basically divided into two types, single wall CNTs and multiple wall CNTs. The single wall CNTs are further divided into different types depending on the relation between n and m of chiral vectors. These are armchair CNT where m is equal to n, the zigzag CNT where m is equal to 0, and the rest are called just chiral CNTs. The multiple wall CNTs can be either metallic or semiconducting depending on their geometry, that is chirality and diameter. The figures show how a single wall CNT looks depending on the chirality. The first figure shows the representation of a chiral vector. The second figure shows a zigzag CNT. The third figure is the chiral CNT, and the fourth figure is an armchair CNT. Now let's talk about how CNTs form. Nanotubes or fullerenes grow under certain growth conditions from carbon. They are cylindrical in shape. The finite size of the graphene layer has dangling bonds. These dangling bonds correspond to high energy states. The nanotube form by eliminating these dangling bonds and increasing the strain energy so as to decrease the total energy. How are they made? CNTs are basically made by arc discharge and laser ablation. Other methods through which CNTs are created are chemical vapor deposition in natural, incidental, and controlled flame environments. In arc discharge, CNTs can be found in the carbon soot of graphite electrodes during an arc discharge involving high currents. This process yields CNTs with lengths up to 50 microns. Laser ablation is the process in which a pulsed laser vaporizes a graphite target in a high temperature reactor while an inert gas is inserted into the reactor. The nanotubes develop on the cooler surface of the reactor as the vaporized carbon condenses. Properties of CNT. The Young's modulus of CNT is over 1 terapascal, which is much greater than aluminium NC fiber. The strength to weight ratio is greater than 500 times that of aluminium. Similar improvements are seen over steel and titanium. One order of magnitude improvement is observed over graphite or epoxy. CNTs have the strongest tensile strength of any material known and the highest modulus of elasticity. Maximum strain is approximately 10% higher than any other material. Thermal conductivity is approximately 3000 in the axial direction and a small value in the radial direction. Electrical conductivity is 6 orders of magnitude higher than copper. It has a very high current carrying capacity. Implications of CNT in electronics. First of all, the carrier transport is one-dimensional. All the chemical bonds are satisfied, and the CNT electronics are not bound to use SiO2 as an insulator. High mechanical and thermal stability and resistance to electron migration is observed. The current densities up to 10 to the power 9 amperes per centimeter square can be sustained. Diameter is controlled by chemistry and not by fabrication. Both active devices and interconnects can be made from semiconducting and metallic nanotubes. We just discussed about one-dimensional transport. Due to their nanoscale dimensions, electron transport in carbon nanotubes will take place through quantum effects and will only propagate along the axis of the tube. Because of this special transport property, carbon nanotubes are frequently referred to as one-dimensional. Electrical properties. If the nanotube structure is armchair, then the electrical properties are metallic. If the nanotube structure is chiral, then the electrical properties can either be semiconducting with a very small band gap, otherwise the nanotube is a moderate semiconductor. In theory, metallic nanotubes can carry an electric current density of 4 × 10 to the power 9 amperes per centimeter square, which is much greater than 1000 times that of metals such as copper. There is a property that is so strange and interesting about CNT. While passing an electrical current through the carbon nanotube, the researchers found that there is a property so strange that they had to coin a new name for it. It was called the remote joule heating. The CNTs are conductors like metal wires, so when current passed through them, researchers expected that they would heat up. But instead, they remained cool and the materials around them got heated up. That strange property of CNT is what made the researchers think that it could be used in the transistors. Now let's talk about CNT field effect transistors. The CNT FETs use carbon nanotubes or an array of carbon nanotubes as a channel instead of the bulk silicon in traditional MOSFET structure. There are different types of CNT FETs. They are backgated, where high contact resistance is present and it is difficult to switch devices on and off during low voltages. There are top-gated CNT FETs, where the structure is similar to the conventional MOSFETs. The wrap-around gate CNT FETs have the entire circumference of nanotube as a gate. This improves their electrical performance, reducing the leakage current. The suspended FETs have the entire device fabricated first, and the oxide is etched down in the center to provide a trench, and tubes are grown and suspended over the trench. The graphs shown in the slide represent the VI characteristics of CNT FETs. We can see that they are similar to the traditional MOSFETs. Coming to the applications of CNTs, nanotubes hold the promise of creating novel devices such as carbon-based single-electron transistors that significantly are smaller than the conventional transistors. They're useful in many applications in nanotechnology, electronics, optics, and other fields of material science and architectural fields. Nanotubes have excellent strength-to-weight ratio that creates the potential to build an elevator to space. They can also be used in quantum computing, where the nanotubes can be filled with molecules that have either an electron or structural property which can be used to represent the quantum bit of information and which can be associated with other adjacent qubits. They are also used in plastic electronics, flat panel display, and they can replace copper as via and interconnect. Coming to the electrical applications of CNTs, they can be used in field emission in vacuum electronics and other applications in electrodes and capacitors. The field emission display uses electron beam to produce images which traditionally used to work on cathode ray tubes, but recently the focus has been shifted to carbon nanotubes. And coming to energy storage applications, they can be used in lithium batteries and hydrogen storage. In lithium batteries, nanotubes are used because of their highest reversible capacity of any carbon material known, and they have intrinsic characteristics desired in material used as electrode in batteries and capacitors. Coming to the hydrogen storage, single-walled carbon nanotubes store hydrogen, and the nanotube technology will meet the challenge of storing hydrogen and releasing them adequately in a hydrogen fuel car in future. It also has some biological applications such as sensors, AFM tips, and DNA sequencing. There are also a number of risks and defects associated with the CNTs. Defects can occur in the form of atomic vacancies. High level of such defects can lower the tensile strength by up to 85%. Because of very small structure of the CNTs, the tensile strength of the tube is dependent on its weakest segment. Carbon nanotubes shorter than about 200 nanometers readily enter into human lung cells similar to the way asbestos does, and this may pose a risk to health. Carbon nanotubes, along with the majority of nanotechnology, are still an unexplored matter, and there are many possible health hazards that may be linked with it. These are the references that I used to put the presentation together. Thank you.